Good day, everyone, and we meet yet again. And I know that you've been working hard trying to prepare for those preliminary exams or even your final exams. And so today I just wanted us to continue in our revision and shout out to Hulisani, who has sent me. In fact, she's been begging, oh goodness, for so long, for me to do these questions that involved hot air balloons. So, if you haven't subscribed, please do the right thing, okay? And welcome to the family. And so, I'm going to be tackling this question today, but please, I'm going to be doing this a little bit differently. So, what I want to do is I have drawn this question in a sense, on the paper here, but I'm going to be narrating through the story. Okay, it's from a previous past exam question. I'm not too sure which one, but yeah, it does look something like this. So first of all, they say to us, a hot air balloon is rising vertically at a constant velocity. So this involves a hot air balloon that is rising. Okay, so there's our hot air balloon. It's going vertically upwards. Okay. And then they say to us, when the hot air balloon reaches a point A, which is that point over there, all right, which is a few meters above the ground, a man in a hot air balloon drops a ball which hits the ground and bounces. Ignore the effects of friction, of air resistance rather. Okay, so in this case, when we get to that height, we don't know what height that is above the ground. Okay, let's call that height h. Okay, so there they drop a ball there, the man drops a ball. Okay, and then now they say to us the velocity time graph, okay, below, okay, which is this one that I've drawn here, represents the motion of the ball from the instant it is dropped until it bounces for the first time. Okay, the time interval between the bounces is ignored. Okay, and the upward direction is taken as positive. Okay, so now we're going to use the information on the graph to answer the questions that are going to follow. I didn't write the questions down. I'm going to be taking you through this. Okay, so before we get to the questions, what I wanted us to do was to look at exactly what is happening. So I want to relate what's happening to the ball itself, and I want to kind of relate that to the graph that we see over there. Now, first of all, ladies and gents, I want you to know that when we've got a situation where we've got a bouncing ball, okay, I'm just going to shift this a little bit. So first of all, okay, let's talk about this ball that is released over there. So in as much as they said that the ball is dropped, now usually we know that when the ball is dropped, okay, we normally say, well, the initial velocity is going to be 0, okay? But remember, in those instances, this is when we drop the ball from either a top of a building or whatever the case may be, top of a bridge. And the bridge or the building is stationary. Okay, but in this case I want you to think about it. When the balloon was rising upwards, the ball was inside the balloon, isn't it? So here we talk about relative velocity. All right, so think about it. So in this case, what was the balloon or the ball doing when it was in the balloon? It was also moving, right, at the same velocity as the balloon rising upwards. So when I drop this ball, its initial velocity will not be 0, but its initial velocity will be the velocity of the balloon itself. All right, I hope that makes sense. So as it was rising, the moment that I drop the ball, okay, it will assume the initial velocity of the balloon, okay? And then what will happen? Now, because the balloon was rising upwards, so the moment I release the ball, the ball is also going to be rising upwards a little bit. Now, of course, I can't draw a moving hot air balloon, you know. But if you just ignore the picture of the balloon, what's going to happen to the ball? It's essentially going to go up a bit. So first of all, its initial velocity will be the initial velocity of the balloon. Of course, I'm not saying that it's going to pass the balloon or whatever the case is. Remember, as I said, I can't draw a moving balloon, but the balloon will continue moving upwards. Okay, so as I release the ball won't immediately go down, but it will first go up a little bit. Okay, all right, reach that maximum height. And in that case, of course, it will come back, all right? And we assume that it's going to go down. And as they said, when it gets to the ground, it's going to bounce, all right? And reach another maximum height and then, you know, just get to the ground. Okay, they told us about only one bounce. So I want to kind of relate what the picture that we see here. Now, please, again, I'm saying this, ladies and gents. I am in no way suggesting that, you know, the ball will go up and pass the balloon. No, no, no. The only reason is because I couldn't draw a balloon that's moving. Okay, hopefully some of you who are into, you know, graphics and all of that will do that for us someday, just to show that as the balloon went up, okay, so the ball would do something like this. Okay, as the balloon goes up, okay, so the balloon also as the balloon rather goes up, the ball will initially go upwards, reach that maximum height, so it will not immediately go down. It would first of all go up, reach that maximum height, and come back down. Okay, so what I want to do is I want to kind of label my points and relate that to the graph. Okay, so we've got position A. So where would position A be on the graph? It would be the initial point where I start. So it would be that point over there. Now note, they've given us that the initial velocity is 5.88. So what does that suggest to us? It means that the initial velocity of the ball is the velocity of the balloon. So in this case, it means that the balloon was rising up at what speed? At 5.88 meters per second. Okay? And then you remember what we said about the ball? As it goes up, it reaches a maximum height, okay, where the velocity is 0. Now look at that velocity time graph. Okay, so we know the speed is going to decrease as it goes up until it gets to 0. So there it is. Starts at 5.88 and it decreases until it gets to 0. So let's call that point B, if you don't mind. Okay. So this is where the ball reaches maximum height. So this would be point B over there. Okay, right. I hope you're still with me. And then obviously we're going to pass the point where the ball was when it was initially dropped. Okay, so that would be point C. Now remember, we call this a time symmetry, right? Because the same time it takes going from A to B would be the same time it takes going from B to C. So you can see from A to B it took 0.6 seconds. All right, it means it would take an additional 0.6 seconds. So this would happen at about 1.2 seconds. Okay, so it would be 1.2. So it means now, once again, the same velocity that it had, or rather I should say the same speed that it had when it was going up, which was 5.88, would be the same speed at the same position when it goes down, right? Okay, so in this case, if it moved at 5.88 at A, it would be 5.88 at C. So, but it would be in the opposite direction, obviously. So in this case, it clearly shows that they must have regarded motion going upwards as positive. So they've actually taken up as positive. How do I know that? Because the ball initially went up and my initial velocity is positive there. Okay, there's something else that we'll use there to show that. So it means there at 1.2 we also have another negative 5.88. Of course, they didn't give us that. We are just interpreting it from the question itself. Okay, right now, obviously, because can you see it reached maximum height at B? All right, so that would be point C over there. Okay, but it went even further from point C, and it went further down. Now, I will regard the moment just before it touches the ground. Okay, so I'll regard that as position D. All right, and then obviously it stops momentarily at position D, and then it bounces, so I'm going to call that position E. Okay, so in this case, now look at this position D. This is when it reaches the ground, so this is at that point over there, just before it touches the ground. Okay, moments, just little moments before it touches the ground, and then it stops momentarily, which is at that point there. Okay, and changes direction, and now remember it was going down, so the velocity was negative, and now suddenly in a blink of an eye it's now going up, and therefore that velocity would be negative. I think we're given that velocity as 2.96. Oh, I hope it's not going to be confusing. Okay, so that velocity over there is 2.96. Okay, 2.94 rather, 2.94. Okay, so we're given that on the actual graph. Okay, I hope you're still following me. My graph doesn't have too many things. Okay, now what's going to happen? Now I'm going to have the ball going up. Okay, so my velocity, once again, it was going up. It's positive, but it's decreasing until it reaches 0. So there's that position E over there. So this kind of vertical line here shows me the moment when the ball bounced. Okay, so I hope that makes sense to you, right? So in this case, we reach another maximum height, which is at they call that position P. Okay, if you want to maintain that as P, so yeah, let's keep that as P. All right, and I'll call this one position F when it comes back to the ground again. There it is over there. Okay, right, so what we want to do is to kind of make an attempt at answering the questions, and I'm going to be taking you through the questions. I hope so far everything that I've said makes sense and I didn't confuse you in any way, right? Now they say to you, write down the magnitude of the velocity of the hot air balloon. Do you see that this velocity time graph had nothing to do with the hot air balloon, but instead it was for this ball that was dropped, okay? But where are we going to get the information for the hot air balloon? Of course, at the initial point, because remember, when this ball was released, it was exactly at that point when it was still with the hot air balloon. So the velocity, the initial velocity of the ball would be the velocity of the hot air balloon. So in answering that, it means that the velocity of the hot air balloon, okay, hot air balloon would be, and they said they only wanted the magnitude of it, so it would be 5.88 meters per second. Okay, I hope that makes sense, right? Okay, so the next question. Before I get to the next question, just something else that we need to know about velocity time graph. Remember, from our previous videos, I showed you how velocity time graph, okay, the velocity, or rather the gradient under a velocity time graph, tells us about gravitational acceleration, right? So look at that gradient there. That gradient is negative, okay, so it's telling us that they've taken up as positive. Remember, gravitational acceleration at any given point for this ball, by the way, is always acting vertically downwards. So at any given point, remember that gravity acts downwards. The only time where, our acceleration will change would be at that point when it touches the ground there, which in this case, it would not be under vertical projectile motion. It wouldn't be under free fall because there's another force other than gravitational force. Okay, right. So in this case, what we're simply saying is that the gradient underneath that graph, okay, it would actually be the acceleration. So it would be minus 9.8, right? And the only reason why it's negative 9.8 is because we've taken up as positive, okay? Right, now they say to us, calculate the height above the ground from which the ball was dropped. So what they are simply saying is that how far is height h, okay? And now we're going to use the graph to kind of answer that question, all right? Now height h, please, I want you to follow me carefully. So in this case, I can now calculate the displacement. And what is displacement? It's the straight line change in position from beginning to end point, right? So between A and D, right? Okay. What is the change in position in a straight line? It is exactly that height h there. So I am going to now regard, or I'm going to actually take the change in position between A and D. Now, because they said I should use the graph, I want to just show you quickly. I did say that, remember that the area under a velocity time graph actually tells you about displacement. So what I'm going to do is let me find the area between which points? Between point A and point D. So where is that? So the area under this graph, can you see that it's going to be this triangle over here to D, which is also the area under that triangle over there. Okay, so I'm going to say, well, it's going to be area. I'm going to take the area, which is equal to, right, the area underneath that triangle is a half base multiplied by perpendicular height. Okay, you mathematicians would know that. All right, plus, okay, remember we're looking between A and D, so the area underneath the graph, this would be that little triangle over there, plus that little, that bigger triangle over there. Okay, so in this case, plus another half base multiplied by perpendicular height. Okay, so I would therefore say, what is the base of my triangle there? It's between 0 and 0.6. So what would that base be? That would be 0.6, okay, multiplied by the perpendicular height, and my height in that case is 5.88. Remember, at A there, it's 5.88, okay? 2.94 is for that height over there. Okay, so this would be between 0 and 5.88. So this would be 5.88. Okay, right. And I'm going to add to that, okay, half base. And what is my base now for the next triangle? Now, please, I want you to be very careful, okay? I know many people would quickly say, well, it's 2.6. Remember, you're talking about the distance between that B and that point there. Okay, so it's 2.6 minus 0.6. Can you see that? So in this case, it would be 2, okay, multiplied by the perpendicular height. And again, the perpendicular height is between 0 and minus 19.6. Okay, so that's minus 19.6 over there. Okay, and in this case, what would we get for our calculation? Okay, and I get a value of minus 17.84. Okay, you can just verify that for me. So that's minus 17.84. 0.84, and remember that's in meters. So it means that it was displaced from A till that point there, 17.84. So what I want to also do, I don't want to overwhelm you a lot. What you could have also done, okay, but if the examiner insists that you need to use the graph, it means that you need to use the two things, gradient as well as area, right? But what you could have also done is use equations of motion, okay? Where you could have said, well, you've got your initial velocity, which is 5.88, and you know your final velocity at that point there, which is minus 19.6. Okay, you know gravitational acceleration is minus 9.8. It would be negative because you've taken up as positive, okay? And you need to now look for the displacement, okay? I suppose you could have used the second equation. The VF squared is equals to VI squared plus 2 times A delta X, but I'm going to change that to delta Y because we're talking about that one there. Our final velocity was minus 19.6 squared. Okay, initial velocity, that was 5.88 squared, okay, plus 2 times. Now note, gravitational acceleration is acting vertically downwards, so that's minus 9.8 there, multiplied by our displacement. And all that we need to do is some mathematical gymnastics. Okay, so I would have taken that minus 19.6. Remember to put that in brackets, squared, okay, minus 5.88 as I calculated, and thereafter divide by a negative 19.8, and I get exactly the same answer, which is delta y would be minus 17.84 meters. And the reason why it's negative, remember, in this case it's telling us that this was displaced downwards. Remember, we've taken up as positive. Okay, ladies and gents, I hope that I haven't lost you. You're still with me. Okay, so in this particular case, I want you to please note that when we take such a question, okay, we normally would be asked to use the graph to try and answer the question. So remember that in a velocity time graph, okay, the area underneath the graph actually gives you displacement, okay? Whereas if you take the equations of motion, you can still do the same thing. Now, I know what some of you may possibly be thinking. You're thinking to yourself, but what about the fact that the ball went up and then went down? It seems like I've disregarded the motion of the ball going up, but no, I haven't. Remember, between A and C, what would be the total displacement? It went from a position, went up, and came back to the same position. So the total displacement between A and C would be 0, right? Because it's exactly where it started. So suppose, I don't know what the displacement is going up. Suppose it went 5 meters up. So it would be 5 meters minus another 5 meters, right? So therefore it means that displacement would be 0. And that's why we say the total displacement between A and D, it would just simply be the straight line change in position between A and D. So it would be just the straight line, the height there. Okay, right. Now let's move on to the next question. Ooh, I didn't want this video to take too long. Okay, I wanted you to understand the question rather. Okay, now the second question asked is calculate the time P indicated on the graph. Okay. Now, time P, this is the time, okay, between just after the ball bounced and until it comes back to the ground. So P would be the time when it reaches that maximum height. It's that time over there, right? Now, what I want you to keep in mind is that time P, remember, for this motion here, this would be again a time symmetry. Why? Because it moves here, or it leaves at this point from a certain position and it comes back again to the same position. So what do I know? It means that the initial velocity here would be the same velocity with which it returns to the ground. Okay, so not velocity, rather speed. Okay, because remember, velocity involves direction, right? So what was the speed with which it left point E? It left at 2.94. So it means that it would come back. Can you see that? Okay, it would come back to the ground again at the same speed, which is 2.94. The only difference is that it's negative now. Okay, so again, what we know is that the time that it takes going up would be the same time that it takes coming down. Okay, so I was told that it left at 2.6 seconds and it came back at 3.2. So what would be that time there? Of course, it would be the mean, okay, between the 2 points. So all I can simply do is just say 3.2, okay, 3.2, and add it to 2.6. And remember, to get the mean, I need to just divide that by 2, and I get a time of 2.9 seconds. So the time there would be 2.9 seconds. Okay, right. And how did I get that? I added this to that and I divided it by 2 to get the mean there, right? Another way that you could have just considered it is that, well, the total time between those 2 points would be the difference there, which is 3.2 minus 2.6, okay, which would give you 0.6. So it means that for it to come back from, after the bounce and until it comes back to the ground, it took 0.6 seconds. But then how long did it take to get to point P? It took 0.3 seconds. So all you could have done is that you could have said, okay, from 2.6, I add 0.3 seconds. And so therefore it means it would have taken 2.6 plus 0.3, which would have given you 2.9 seconds. I hope you're still with me. Okay. And then let's get to the next question. They say, calculate the maximum height the ball reaches after the first bounce. Okay, so they want to find out what is the height it reached, okay, after the first bounce. Remember, where's our first bounce? Okay, so in this case, this is when it left, so we want to know. So we would kind of get the area underneath that graph again, right? Okay. I would have hoped, we would have used something that would give us, the gradient, or just require us rather to use the gradient. But nonetheless, okay. So I would get the area underneath that graph again. Or you can say, well, I know my initial velocity, I know my final velocity, right? And I know what gravitational acceleration is. It's minus 9.8. And so you can get that height there above the ground. Okay, so what you can simply do, I'm going to take the area. So the area, remember now I'm looking for that height there, and I'm going to say, well, it's half base times perpendicular height again. Okay, I suppose if you didn't know this, now you do. Okay, so what would be the base here? Remember, it's between 2.6 and 2.9. So the base here, that would be 0.3 multiplied by the vertical height, the perpendicular height, which in this case it's from 0 to 2.94, which is positive 2.94. Okay, and in this case, we get a height of 0.44 seconds. Okay, meters. All right, so that would be my height there. And again, as I did say, you could have used again the second equation and said, okay, my final velocity would be 0. Okay, my initial velocity would have been 2.94, and gravitational acceleration minus 9.8, and I bet you would get the same answer there. Okay. All right, now let's get to the conclusion. All right, now they say to you, calculate the distance between the ball and the hot air balloon when it is, or when the ball is at its maximum height after the first bounce. Whoa. So they want to know, okay, how far would the ball be from the air balloon? Okay. Now, one thing that I want you to always keep in mind. So I already know the ball would be, 0.44 meters away from the ground. Okay. It's that distance over there. It's 0.44, right? But remember, as the ball went through all of this motion, what was the air balloon doing? Okay. They told us that this air balloon is moving vertically upwards at a constant speed. Okay. So from the moment that the ball and the air balloon were separated, the air balloon kept on going upwards at a constant speed. So I want you to keep in mind. So it means that the hot air balloon is not under free fall. It's not a projectile. It's not under projectile motion, right? Why is that? Because gravity is not the only force that's acting. So it has an acceleration of 0. Why do I say acceleration of 0? Because it is moving at a constant speed. Okay. So now, if you don't mind, ladies and gents, we're kind of out of space. So I'm kind of going to work on this side. I hope you don't mind. Okay, so what I'm going to do is I'm going to say, well, how long since it was separated from the ball did the hot air balloon keep moving up? Okay. Now remember, it was already 17.84 meters above the ground, okay? Right? So how far did it actually keep moving upwards? So I'm going to say, all right, so let's take delta y is equals to vi delta t. Now remember, I'm now looking at the hot air balloon, right? So I'm going to say vi delta t plus, remember we say half a delta t squared. Okay. Some of you who are doing IEB, remember you use s is equals to ut plus half at squared. Remember, this is exactly the same thing. Okay, use initial velocity, blah blah blah. Okay, so this is exactly the same thing, right? So all that we're simply saying is that delta y, okay, we are looking for the distance that the balloon kept moving up. Okay, but what do we know about the acceleration of the hot air balloon? It is 0. So this entire term, okay, can just simply disappear because our acceleration is 0. The hot air balloon was moving at a constant speed, right? So now it means that delta y would be what's our initial velocity, or what would be the velocity of the air balloon. Okay, it would be 5.88, okay, upwards. But now let's resolve the time. How long did it take for the ball to reach this height here? You remember it took, since it was separated from the hot air balloon, it took 2.9 seconds. Okay, so it means that the time that would use there is 2.9. Why is that? Because remember, as the hot air balloon, as the ball kept on bouncing, if you had a stopwatch or you had something to measure the time, you'd see that after that, when it reaches the second maximum height, it would actually have taken 2.9 seconds. So as a result, the hot air balloon kept on moving during that time. So I'm going to take that. So that's 5.88 multiplied by 2.9. And that gives me 17.05. Okay, so it means that the balloon moved a further 0.05 meters. Okay, all right. Now remember, okay, it was already 17.84 meters above the ground. But as the ball kept on doing, going up, going down, and all of that, the balloon therefore moved a further, okay, 17.05 meters. Okay, so how far is the hot air balloon now? It is actually 17.05 plus that 17.84 meters above the ground. Okay, so that's 34.89. Okay, so it means the hot air balloon has reached a height of 34.0.89, sorry about that, meters. Okay, but that's not what we were asked. They said, how far is the hot air balloon from the ball, right? They said calculate the distance between the ball and the hot air balloon when the ball is at its maximum height. So we want the distance between those two there. So it is 34.89 meters above the ground. We're going to subtract that 0.44. Okay, so we want the difference there. I hope I could, I wish I could actually just illustrate it better. Okay, so we want the distance between those two, remember? So the hot air balloon from the ground, this distance here is 34.89. And we want to know the distance between those two, so I'm going to say 34.89 and I'm going to subtract that distance there, which is 0.44, and it would give us that distance there. So in this case it means that the distance, okay, and sorry about all of this mess here, I didn't have enough space to write that. So the distance between, okay, would be 34.89, and I would subtract 0.44, and that should give us 34.45 meters. Okay, right, I hope that makes sense, ladies and gents. I just want to conclude this question, even though we weren't really asked to do this. If, let's say, the examiner had asked you to draw a position time graph taking the ground as your reference. So I'm going to try and use this little space over here to illustrate what that would look like. So suppose you were asked to draw a position versus time graph, for the motion of this ball, and how would that look like? Okay, for the motion of this ball. From the time that it was released up until it reaches the ground for the second time. Okay, so what would that position time graph look like? Well, I would say, it would start at 17.84. Remember, if we take that 17.84, sorry about that, I'm trying to squeeze everything in. Okay, so it would start at 17.84. Okay, and what would happen? Okay, it went further up. We don't know how far up it went. Okay, so it went further up, it reached the maximum height, and then what happened? It came back down, touched the ground, and then upon touching the ground it bounced, reached a next maximum height. We know now that maximum height, okay, it would have been actually very small. Okay, sorry, it's not drawn to scale, but I hope you understand that. So that would be 0.44 there. Okay, that's our second maximum height. And then what would happen? It would now get to that point there. So if you wanted reference in terms of time, we know we got to the maximum height at 0.6. Okay, it bounced at 2.6 there. And remember, they said we should disregard that little moment when it bounces, right? And then we know the second maximum height would be at 2.9, and the total time would be at 3.2. And remember that this would be position, okay? So remember, your position is in meters, okay? And that would be your time in seconds, okay? Right, so ladies and gents, I really have tried my best, okay, to try and take you through this question. I know that there's a lot of writing over here, but I hope nonetheless it would make sense, all right? And to you, as you prepare, towards your exams, I hope that this will make a huge difference. All right, and please keep those questions coming. I'll try to address them as much as I possibly can, but right, if you haven't subscribed, please make sure that you are part of the family. All right, we've got a lot of learning to do. Otherwise, I'll see you guys again next time. Sharp, sharp.